All right, welcome ladies and gentlemen. This is the video on standard enthalpies of formation and using standard enthalpies of formation to determine delta H. So this is the last in our flip lessons. So enthalpies of formation, first of all, we'll do the formation bit and then the standard bit. Enthalpy of formation is the heat that's associated with the formation of a compound. So it's great. It's a very descriptive name. We like descriptive names in chemistry. They sort of tell us what it is. So that's all it is. We're making a compound from its constituent elements. That's important, that we're not making this compound from other things. It's about the formation of a compound from elements, and it will always be that way. We abbreviate it. We show the symbol as delta HF. F for formation. Oh, wow, go figure. The thing about delta HF formation is it's almost always negative. Not always, but almost always. Because, and you might remember this, but you might not, if you're forming a compound, that means that you are creating a bond where there wasn't a bond there before. And the whole reason that atoms bond is to have a lower energy. That is what drives atoms to bond and to form compounds, because they are at a lower energy when they're bonded than when they're by themselves. So typically that means that they will be releasing energy in the process. So nearly all delta H's of formation are negative because bonding is the bonding process releases energy. If you ever see a compound that has a positive delta H of formation, that actually indicates that the compound is pretty unstable because it's at a higher energy when it's bonded than when the elements are separated. So standard enthalpies of formation are simply taking this idea of forming a compound from its constituent elements and looking at it under certain conditions, under standard conditions. And remember, standard conditions when it comes to thermodynamics are 1 atmosphere, 1 molar, 25 degrees Celsius. It's not the same as STP. The pressure is the same, the temperature is not. And the elements that you form the compound from have to be in their standard states. So we wouldn't be talking about forming carbon dioxide from diamond carbon because that is not the sort of the natural state of carbon. Instead, we'd be forming carbon dioxide from graphite. That is the standard state. Likewise, if we're forming carbon dioxide, we would not be forming it from solid oxygen. That is not the standard state of oxygen, the natural state of oxygen. The natural state of oxygen would be O2 gas. And the most important bit of this, actually, the one that the AP really likes to ask about, is standard enthalpies of formation. You're only making 1 mole of the compound, and that's it. So you kind of have to think about what amount of each element, what coefficient for each element you're going to need in order to make just 1 mole of the compound. Now, the standard enthalpy of formation is delta HF naught. Again, there's that NaUGHT. And for an element, delta HF naught will always be 0, because the definition of delta HF is the formation of something from its constituent elements. So we'd be talking about making O2 gas from O2 gas. There's no change. Nothing has changed here. So there is no heat that is exchanged, right? Delta H for this is 0. Nothing changed. So don't get tripped up, because there will oftentimes on multiple choice questions that deal with standard enthalpies of formation, they'll give you some information and they'll be like, hey, figure out the delta H of this reaction using delta HFs. And there'll usually be some choice along the lines of, it cannot be done because you didn't give us the delta H of formation of oxygen, or the delta H of formation of nitrogen, or the delta H of formation of carbon. That's there to trip you up. That is not the correct answer. That is not the correct answer. That is not the correct answer. You don't need to be given the delta H of formation of an element, because you know that the delta H of formation of all elements is 0. 0. Now, delta H's of formation, these are reference values, meaning you don't memorize them, you utilize them. And Appendix 4 in your textbook has tons and tons and tons of delta HF values for different compounds and different phases of matter. So we are basically going to be using Appendix 4 when we do our problem set to look up delta HF values of different compounds. Writing, first up, writing the reaction for standard enthalpies of formation. This is actually important. All of those delta HF values in Appendix 4, they actually all coincide with a specific reaction. When you see those delta HF values, they're actually telling you it's for the formation of that compound from its constituent elements. So you need to be able to write these reactions, and this is actually going to be the first question that's on your problem set. I'm going to ask you to write reactions for different, write formation reactions for different compounds. So for example, what is the equation for the formation of NO2? Well, we want to form NO2. That means that NO2 is going to be a product. Now, standard enthalpies of formation, we're making a compound from its elements in their standard states. So the elements that are in NO2 are obviously nitrogen and oxygen. The standard state of nitrogen is N2 gas. So you can't just say N. That is not the standard state of nitrogen. Nitrogen is a diatomic, so standard state is N2. Likewise, standard state of oxygen is O2. Not just O. So we have N2 plus O2 yields NO2. Now you have to balance your equation. This is critical how you balance your equation, because if you balance your equation the wrong way, I mean, even if it's still balanced, but you balance it the wrong way, you won't get this question correct. Because standard enthalpies of formation means that you are only allowed to make 1 mole of a compound. And that is it. Meaning, you have to have the coefficient of your product be 1. You have to. That's it. You have no other option. It's standard enthalpies of formation, meaning you are making 1 mole of a compound, and that is it. That is done. So we're making 1 mole of NO2. That locks you in, and that's going to dictate how you balance the rest of it. So if we only have 1 mole of NO2, that means that we can only have half a mole of N2, and we will want 1 O2, and that right there, this equation right here, when you look up the delta H of formation of NO2 in the textbook, this is the reaction that it's talking about. This is the equation that is giving you that delta HF value. So you have to make 1 mole to meet the definition. So doing another example, write the equation for the standard enthalpy of formation of methanol. That means that we were going to want to put methanol on the product side because we're making it, and we're only making 1 mole of it. And then it's looking at what elements methanol is made of, and it's made of carbon, and it has 1 carbon. So I'm going to have 1 carbon. Carbon is not a diatomic. Remember, we only have certain elements that are diatomics, and the standard state of carbon is graphite. So I am, in fact, going to indicate that. Then I have hydrogen, and standard state of hydrogen is H2 gas. I have 4 hydrogens in CH3OH, so I'm going to put a 2 out in front of that. And then lastly, I have an oxygen. So the standard state of oxygen is O2 gas. But there's only 1 oxygen in CH3OH, so I'm going to have to put a 1/2 there. And that's how you write the reactions. You have to have 1 mole of product. You have to make the compound, so the compound is going to be on the product side, and you are making it from the compound's elements in their standard states. Now, utilizing delta H of formation, how can we use delta HF naught to get delta H for another reaction, a totally different reaction, a reaction that is not a formation reaction? We have an equation. It's fundamentally based on this idea, final minus initial. And it's this reaction right here. Delta H naught for any reaction at all, can be found by summing up your delta HF of your products, by summing up your delta HFs of your reactants, right? That's what the sigma means, sum up, and then subtracting them. Products minus reactants will give you delta H for any reaction at all, So if you're given delta HF values and you're asked what's delta H of this totally different reaction, you're probably meant to use those delta HF values to do products minus reactants. This equation right here is on your reference table. It is in the thermodynamics section. So you have that. You're absolutely told this reaction. Now, explaining that formula just a little bit, basically, why are we doing products minus reactants? Why are we allowed to do the sum of the delta H's of formation of the products minus the sum of the delta H's of formation of the reactants? How does that get us the overall delta H naught? Well, it has to do with this figure right here, realistically. So we have our reactants, and then we have our products. It's based on the idea that in order to go from reactants to products, you have to turn your reactants into their elements. Basically, that you're totally breaking everything down, and you are, instead of forming bonds, you are breaking bonds. This process, this one right here, this is the opposite of delta HF naught, right? To go from a compound to an element. That is the opposite of delta HF. Delta HF is about forming compounds from their elements. So, okay, thermochemistry says, well, what do you do if you flip a reaction? If you do the opposite, you flip the sign, right? So we negate our delta HFs, hence why it's minus the sum of the delta HF of reactants. The minus sign is the negating, because you are doing the opposite process. Then, to go, once you've broken everything down, once you've taken your reactants and you've pulled them all apart into their constituent elements, which is the opposite of delta HF, now you're talking about forming a compound from its elements. This is delta HF. Right? You're going from the elements to the products, from the elements to the compound. That is what delta HF is talking about. So we are not negating delta HF for the products. All we do is we add, hey, you know, what compounds are we making? We're making, in this case, a CO2 and two H2Os. So we're just going to add, hey, you know, what's the delta H formation for CO2 and what's the delta H formation for two H2Os? Add them up. So we are adding. So you basically add your products, you add your reactants, but then you have to negate your reactants, which is why we say it's products minus reactants. So basically you're summing both of them up, and then you're simply subtracting products minus reactants. But that's the idea. That's where that reaction comes, that equation formula comes from. So I'm just going to show you two examples with this. Calculate the standard enthalpy change for the combustion of ethane, C2H6 liquid, to CO2 gas and H2O liquid. So we can do this using Appendix 4. Again, that's where I'm going to be pulling all these numbers from. And we have a balanced equation. So realistically, the first thing that you need to do is look up all these numbers. What are the standard enthalpies of formation for all the species that are in the chemical equation? So just look, and this is where, by the way, the paying attention to phase of matter becomes very important. It matters if you have liquid water versus gaseous water. They will have different standard enthalpies of formation. So pay attention to that. So just pulling the values from Appendix 4. The C6H6 is 49.0 kilojoules. Oxygen, this is an element. Remember, elements have a standard enthalpy of formation of 0. Carbon dioxide gas is minus 393.5 kilojoules. And liquid water is minus 286 kilojoules. Products minus reactants. Sum them up. Okay, so my products, I'm going to start on this side then. Now, my products are CO2 and H2O. So I'm going to have to add together my standard enthalpies of formation of my minus 393.5 kilojoules and my minus 286 kilojoules. But, this is based on stoichiometry. This number is based on 1 mole of CO2. This number is based on 1 mole of water. We don't have 1 mole of CO2, we don't have 1 mole of water. We have 6 moles of CO2, and we have 3 moles of water, which means that when you are solving, you will have to take your carbon dioxide number and multiply it by 6. Because this is really kilojoules per mole reaction, right? But we have 6 moles. We have 6 moles, so you've got to multiply it by 6. Likewise, for the water, I'm going to do minus 286 kilojoules per mole of reaction, but then times 3. And then simply subtract, so that's my products, and then simply subtract the summation of the standard enthalpies of formation of the reactants. So I'm going to try to fit this in. So I'm going to do the C6H6, so that's going to be 49.0 times 1, and I'm leaving off units just to save some space here, plus the 15 halves of the O2 times 0 kilojoules. Yes, you need to write that in. You need to show me that you understand that you are in fact taking the oxygen into account, but the oxygen has a standard enthalpy of formation of 0. This is not hard math. This is adding and multiplying and subtracting. This is not hard. And yet I see students make mistakes on this all the time. You get cavalier about it. You say, oh, well, it's just adding and multiplying and subtracting. And then you mess up. Then you slip signs. You forget order of operations. You get confused about the process. I see more dumb mistakes on this than I do on anything else. So take your time. So I'm actually going to just write out what I get from these individually before I go to the answer. So this you should, and I urge you to do this math so that you hopefully get the same thing as me. Negative 3,219 kilojoules minus, and then again from the reactants, minus 49 kilojoules. So overall, the delta H naught for this reaction up here, simply adding them together, is minus 3268 kilojoules per mole of reaction. Having kilojoules per mole of reaction is always basically a safe bet for a unit for delta H. That's what it's going to be. And then just one more example so that we see how this works. Using standard enthalpies of formation, calculate the enthalpy change for the following reaction. Again, strongly recommend that you simply start by just looking everything up. Sodium, solid sodium. That is the elemental form of sodium. That is the natural state of sodium, so that's going to be 0 kilojoules per mole. The water, that's minus 286 kilojoules. Sodium hydroxide, again, make sure that you're looking up the correct value, the correct phase of matter, because solid sodium hydroxide versus aqueous sodium hydroxide will have different standard enthalpy values, standard enthalpies of formation. So this one is minus 470. And H2 gas, that is the elemental form of hydrogen, so that is 0. Again, we're going to do products minus reactants. Sum up the products, sum up the reactants, subtract them, products minus reactants, take your coefficients into account. So I'm going to do, for the products first, I'm going to do 2 times, right, the 2 for the NaOH, 2 times negative 470 kilojoules, plus 1 times 0 kilojoules. That's my hydrogen, right? It's nothing. It's forming H2 from H2. Nothing has changed. There's been no energy change in there. Minus my reactants, 2 times 0. That's my sodium. Plus 2 times minus 286 kilojoules. That's the water. Again, taking the coefficients into account. That's where those 2's out in front are coming from. Simplifying it just a little bit before I get an answer, which I strongly recommend you do rather than trying to do it all at once. I get minus 940 kilojoules from the products, minus a negative 572 kilojoules from the reactants. So simply adding those together, we get a delta H naught value of negative 368 kilojoules per mole of reaction. And that's it. So you'll see practice problems with this when you come into class on Tuesday on standard enthalpies of formation.